Hello, I'm Changdae from H3. I present our work, BWA-MEM-SCALE, Accelerating Genome Sequence Mapping on Commodity Servers. Kwangwon and Taehoon Kim from H3, Daegyu Han from Kwangwon University, and Jiwon from Hanyang University collaborated this work. Let's start with some background on the genome. Everybody may know about DNA, which stores our biological information. It consists of a pair of strands. The two strands are composed of four types of bases: adenine, cytosine, guanine, or thymine. Since each base is tightly coupled with the one of a paired strand, the two tightly coupled bases are called base pair. Genome is an organism's complete set of DNA. Human beings' DNA is composed of about 3 billion base pairs. Genome sequence is a sequence of the bases which represent a genome. And reference genome is a sample of a full-length genome sequence for an organism. That is, the reference genome sequence has 3.2 billion characters. Then, let me explain genome sequence analysis. The genome sequence analysis is started with DNA samples from organisms, and it is to discover some scientific facts, including the cause of disease. Today's genome sequence analysis involves three steps. The sequencing step amplifies the DNA samples and generates short genome sequences from the DNA samples. In this step, the genome sequences have no location information. Then, the second mapping step maps the generated short sequences to a reference genome sequence and reveals the location of each sequence. Finally, variant calling is used to find the differences between the genome sequence from the DNA sample and the reference genome. The differences are analyzed further by biologists or doctors. In this work, we focus on the mapping step in genome sequence analysis, which is called genome sequence mapping. The genome sequence mapping is to map short genome sequences to a reference genome to find their locations. In computer science terms, this problem is translated as, for all short strings, find the locations in a long string with the lowest edit distance. In other words, this is the inexact string match problem between many short strings and a long string. Here, we translate the mapping problem into the inexact string match problem. This is possible since we have an assumption that genome sequences of an organism are very similar. It is known that DNAs of two human beings are more than 99% identical. Thus, if we find a location that has the lowest edit distance with the short string, the location is very likely to be the mapped location for the sequence. Our goal is to accelerate genome sequence mapping on commodity servers. Our baseline is BWA-MEM-2, which is presented at IPDPS 2019 and is a widely used genome sequence mapping software. In addition, to run on commodity servers, we will not require any special hardware, FPGA, ASIC, processing in memory, processing in storage, or something like that. Before describing our research, I explained the related work. Most genome sequence mapping programs use seed and extend method. Since the inexact string match algorithm is very expensive, they use a kind of two-phase algorithm. First, the seed phase does the exact match with piles of short sequences and a long reference. Due to the high similarity between two genome sequences, this partial exact matching is good for finding candidate locations. Then, the extend phase uses the inexact string match algorithm to compare the candidate locations, and the most similar location is chosen as the mapped location for the short sequence. The overall workflow of genome sequence mapping is presented. First, the reference genome and the indices for seed and extended algorithms are loaded into memory. Then, the genome sequences from DNA samples are loaded from disk. After that, seed and extend pages find the mapping location for each genome sequence, and the formatted output is generated. Finally, the formatted output is written to the disk, and repeat this flow if there are more sequences to read. In the next two slides, I'll explain the seed and extend phases in detail and how the related work accelerates each phase. First, the seed phase is to find the maximal exact matching between a short sequence and a long reference. Most work uses BWT and FM index algorithm for seed phase. I cannot explain the algorithm in a limited time. Instead, I just sketch how the algorithm works. Here is our example reference genome with 13 characters and a sequence with 5 characters for mapping. FM index algorithm builds an index like this. Each row is according to each base of a reference genome, and the bases are sorted alphabetically. The dollar in the first row is appended for FM index algorithm, and I skip the explanation about it. FM index algorithm starts with the last character of the sequence. In this case, it is T. Then, the algorithm accesses the first and last entries of T. The red arrows indicate accesses to the index. By accessing 2 entries, the algorithm can expand the exactly matched sequence to the second last character, C. In other words, the algorithm can find the range of entries of C, which is followed by T. Again, the algorithm accesses the first and last entries of the range. Again, the red arrows point to the accessed entries. Then, with accessed entries, the algorithm can find the entries of G that are followed by C and T. And 2 entries are accessed, and the algorithm finds the entries of A that are followed by G, C, and T. The main performance bottleneck of FM index algorithm is the random memory access caused by working on the index. Several acceleration techniques have been proposed for FM index algorithm. For example, various k-mer index is proposed. With such indices, a work on the index covers k bases in the sequence. Also, some work reorganizes the data structure of the index to make access patterns more sequential. And some hardware accelerators are designed for FM index and algorithm. After seed phase, the extend phase compares the candidate locations using inexact string matching. The widely used algorithms for extend phase are variations of dynamic programming algorithms. BWA-MEM-2 uses a variation of the Smith-Waterman algorithm. This kind of algorithm needs to populate a matrix with scores. This requires heavy computations. Therefore, several work implement SIMD-optimized versions of the algorithms, and many FPGA or ASIC-based accelerators are developed for the algorithms. In addition, some work proposed pre-alignment filtering techniques. They filter out candidate locations with simple computations and run the dynamic programming algorithm only for the high probability candidate. Our question is how to accelerate the genome sequence mapping further. It seems that there is little room for software-only approaches thanks to many prior work. In addition, since we target the commodity servers, we cannot use any special hardware, which is hard to deploy. Instead, we exploit the remaining memory in the system. Most computers have idle memory and list few gigabytes, since memory capacity is determined based on peak usage. In addition, memory is very easy to deploy, and adding memory is much cheaper than attaching FPGAs or ASICs. Thus, we propose BWA-MEM-SCALE, which accelerates genome sequence mapping by using the remaining memory in the system. We start from BWA-MEM-2, a widely used genome sequence mapping program. It is a successor of BWA-MEM, the representative genome sequence mapping program, and provides up to 2.4 times speed up compared to BWA-MEM by architecture-aware optimizations. BWA-MEM-SCALE exploits the available memory to accelerate genome sequence mapping. To exploit the available memory, we propose 2 mechanisms: exact match filter and FM index accelerator. I will explain them later. We also apply a recently proposed mechanism, enumerated radix tree. In addition, BWA-MEM-SCALE provides memory scalable performance. That is, more memory is provided, more performance is provided. On the other hand, even though the remaining memory is a few gigabytes, BWA-MEM-SCALE improves some performance using the limited remaining memory. Moreover, BWA-MEM-SCALE exploits all CPUs fully to optimize genome sequence mapping. It adds several optimization techniques to the whole pipeline and allows the proposed acceleration mechanisms to achieve the maximum end-to-end performance improvement. Finally, in our experiment, BWA-MEM-SCALE provides up to 3.3 times speedup compared to BWA-MEM-2, which already provides 2.4 times speedup compared to the original BWA-MEM. From now on, I'll explain our acceleration mechanisms and optimization techniques. First, I explain exact match filter, which exploits the remaining memory to speed up genome sequence mapping. As I mentioned before, there is a high similarity between the DNA of two human beings, and this is why we can map the short sequences using inexact string matching. Moreover, such a similarity makes that many of the short sequences are exactly matched to the reference genome sequence. In our dataset, 67 to 76% of the sequences are exactly matched to the reference genome. Exact match filter is a cache of mapping information for exactly matched sequences. For a given short sequence, if exact match filter index has an entry for the sequence, it bypasses seed and extend phase and directly generates output based on the mapping information of the exact match filter index. On the other hand, if a sequence has some difference from the reference genome and exact match filter index does not have an entry for the sequence, BWA-MEM-SCALE runs the normal seed and extend phase and finds the mapped locations. Since the exact match filter filters out the exactly matched sequences and skips the most of computations, it accelerates the mapping procedure. Exact match filter index consists of two tables, a hash table containing mapping information and a multi-location table containing additional mapping information if a sequence is located multiple times in the reference genome. To build an index, we generate sequences from the reference genome in a sliding manner. The figure shows an example. The first sequence has the first 5 characters of the reference genome, and the second sequence has the second row's 6 letters. Then the generated sequences are inserted into the hash table. The hash table size is fixed as the reference genome length multiplied by 1.1 to reduce the hash collision. This hash table has two types of hash collisions. The first case is that 2 or more sequences have the same hash value. This is the common hash collision. In this case, we use in-place chaining. We use the empty entry for the mapping information and link the entry to the entry with its hash value. The second case is that 2 different locations have the same sequence. In the figure, the second sequence and the second to last sequence have the same characters. In this case, we should merge 2 mapping information. To reduce the hash table size, we use a separate table called multi-location table. Except for the first location, we insert the location information in the multi-location table, and the hash table entry has a link to the multi-location table entry. In this slide, I discuss the pros and cons of exact match filter. One of the advantages of exact match filter is that only part of exact match filter index works. We bypass the seed and extend phase only if the hash table entry is found. Thus, if the hash table entry is not found for whatever reason, we just do the normal mapping procedure. Thus, partial index works, and this provides memory scalable performance. One of the disadvantages is that exact match filter omits the suboptimal mappings. As the hash table contains the sequences from the reference genome, it cannot find similar but not exact mappings. However, it can find all of the optimal mappings thanks to the multi-location table. The final mapping locations of a BWA-MEM-SCALE are identical to BWA-MEM-2, and the details are in the paper. In addition, exact match filter index should be built for each sequence length. This can be a burden if various lengths of sequences are analyzed. However, generally, most sequencing machines generate the same length of sequences. Thus, one index is enough for exact match filter. Our second acceleration mechanism is FM index accelerator. This accelerates FM index algorithm in the seed page. FM index accelerator caches the result of the first 13 steps of FM index algorithm. In the seed page, BWA-MEM-SCALE first gets the intermediate result from FM index accelerator, and then continues to FM index algorithm with the cached intermediate result. The figure shows an example working of FM index accelerator. In this example, FM index accelerator caches the 2 steps of FM index algorithm. With one-time access to FM index accelerator, we know what entries are used for the next step. Then, FM index algorithm continues with the intermediate result. As a result, FM index accelerator replaces 26 random memory accesses with single index access. Next, I explain the selective index loading mechanism, which provides memory scalable performance using our acceleration mechanisms. The selective index loading chooses the best performance acceleration mechanisms for a given memory capacity. The left table shows the list of indices of BWA-MEM-SCALE. The first two indices, reference genome and FM index, are the same as BWA-MEM-2, and these two indices are used in the normal mapping procedure. The index of FM index accelerator is 1.5 GB and improves the end-to-end performance by about 3%. Exact match filter index is in total 54 GB and shows 125% performance improvement. Last, we also adopt enumerated radix tree presented at ISCA21. The enumerated radix tree provides a multi-k-mer index for seed phase and improves the end-to-end performance by 33% with 60 GB of indices. Originally, enumerated radix tree paper is based on its FPGA implementation, but we apply only its software implementation. In addition, since the enumerated radix tree replaces the seed phase, when enumerated radix tree is used, FM index and FM index accelerator can be removed from memory. The final decision of our selective index loading mechanism is presented in the right table. The minimum index size of BWA-MEM-SCALE is 17 GB. This is the same as BWA-MEM-2. With 17 GB, BWA-MEM-SCALE only uses reference genome and FM index. If 2 GB are additionally available, BWA-MEM-SCALE applies FM index accelerator. Then, when more memory is available, BWA-MEM-SCALE applies exact match filter partially up to 72 GB. When 73 GB of memory is available for indices, all exact match filter index can be loaded into memory. Since enumerated radix tree does not support partial loading of indices, the decision of selective index loading is not changed until 120 GB of memory. Then, finally, when 121 GB of memory is available, enumerated radix tree scheme can be used and replace FM index and FM index accelerator. This selective index loading mechanism provides memory scalable performance. In addition, although system memory is limited, selective index loading provides the best performance for a given memory capacity. From now on, I explain how BWA-MEM-SCALE exploits the whole CPUs to optimize genome sequence mapping performance. I start with motivation. BWA-MEM-2 uses two pipeline threads with three stages: read, map, write. The read stage reads the sequence file from disk and parses the sequence file. The mapping stage includes seed and extend phase, and the write stage does disk write of the output. Among the three stages, only the map stage can utilize multiple cores. However, since the map stage is much longer than read and write stages, two pipeline threads are enough to maintain high CPU utilization. However, for BWA-MEM-SCALE, the map stage is accelerated by exploiting the available memory. The shortened map stage results in some speed up, but the pipeline is not dominant by the map stage and sometimes shows low CPU utilization. Therefore, we optimize the whole pipeline as follows. First, we balance the pipeline. We increase the number of pipeline threads to 3 to match the number of stages. In addition, we reserve cores for each pipeline thread to make read and write stage finish before the map stage of the other pipeline thread finishes. Second, we optimize the read stage by a read-ahead thread. Read-ahead thread is a separate thread that does disk read only. And the read stage only parses the sequence file, which is loaded by the read-ahead thread. Also, we use the chunked memory allocation for internal buffers of a read stage. Last, we also optimize the write stage using a batched system call. This slide shows the effect of pipeline optimization. There are 4 threads, read-ahead thread, and 3 pipeline threads. Read and write stage are also shortened and always finish before the map stage of other pipeline thread is finished. As a result, the CPU utilization is almost always high and the additional speedup is gained. Additionally, we add 2 optimizations to BWA-MEM-SCALE. First, we implement in-memory index store. This preloads the indices on process shared memory. And at the start of a BWA-MEM-SCALE execution, it does not load the indices. Instead, attach the indices in the process shared memory. Since a dataset for an individual has about 1,000 files, the same index should be used 1,000 times. Thus, one-time index loading on in-memory index store can eliminate 1,000 time index loading. Second, we apply huge page for indices. We use 1 GB page for indices. This reduces the number of TLB misses as well as page walk latency. Now, I will show our evaluation. For the evaluation, we use dual scan machine with Intel Xeon CPUs. The memory size is 384 GB, and this is enough to apply all of our acceleration mechanisms. For dataset, we use a sequence file used by BWA-MEM-2 paper and a set of sequence files from Genome in a Bottle Consortium. 871 files of sequencing data represent a sequence data of a human being. For the reference genome, we use HG38. We compare the performance of our implementation to BWA-MEM-2. This graph shows the effect of the acceleration mechanisms. In this experiment, we used the dataset from BWA-MEM-2 paper. The x-axis shows the baseline and what mechanisms are applied, and the y-axis shows the execution times for bar graphs and the speed up compared to the baseline for the line graph. In the bar graph, the colors represent the execution time of each part of the program, as indicated at the top of the graph. RW wait indicates the waiting time for map stage due to the previous read and write stages. Let's see the first bar showing the execution time of BWA-MEM-2. There are some RW wait time and index loading time. In the second bar, our optimization techniques to exploit CPUs removes the RW wait time. Also, in-memory index store removes the index loading time. This results in 31% of performance improvement. The third bar shows the results of applying FM index accelerator. It affects only seed time, and about 3% of performance is improved. In the fourth bar, exact match filter reduces time for all map stages. The total performance improvement exceeds 120%. The last graph shows the result with enumerated radix tree. Since the enumerated radix tree totally replaced the seed phase, FM index accelerator is removed. In the graph, enumerated radix tree additionally accelerates the seed phase and improves the end-to-end performance by 46%. The second evaluation shows the effect of a selective index loading scheme. In this graph, the x-axis shows the baseline and the index size limit for BWA-MEM-SCALE. For example, 70 GB means that the total memory capacity for indices of BWA-MEM-SCALE is limited to 70 GB. The y-axis represents the memory usage of the execution. Now the colors indicate each index. The graph also shows the speed up compared to the baseline as before. The second bar shows the result of a BWA-MEM-SCALE with the minimum memory size requirement. The memory size for indices is the same as BWA-MEM-2, but the BWA-MEM-SCALE uses more internal buffers. The total memory usage is increased by about 5 GB, and 30% of performance is improved. When the memory limit is increased to 20 GB, BWA-MEM-SCALE applies FM index accelerator and gains some performance improvement. If more memory can be used for indices, BWA-MEM-SCALE uses part of exact match filter index. Part of exact match filter index improves the performance by about 2% per gigabyte. When the memory limit is more than 80 GB, BWA-MEM-SCALE does not change the index selection until 121 GB of memory is given. And finally, with 121 GB of memory, BWA-MEM-SCALE applies enumerated radix tree and removes FM index accelerator and gains additional 49% of performance improvement. This is the last evaluation in this presentation. This experiment uses a sequencing data set of an individual. The dataset consists of 871 files and has about 6 billion sequences. In the graph, x-axis shows the baseline and the index size limit for BWA-MEM-SCALE. For this experiment, I show 3 representative points of the index size limit. The y-axis shows the execution times for bar graph and the speed up compared to the baseline for the line graph. In this graph, index loading time is also included for BWA-MEM-SCALE. The index loading time for BWA-MEM-SCALE is the pre-loading time on in-memory index store. Let's compare the first and second bar graphs. Compared to BWA-MEM-2, BWA-MEM-SCALE with 17 GB of indices accelerates the execution time by almost 2 times. The main reason is the reduced index loading time. Since each file of the dataset is relatively short, the portion of index loading time is large for BWA-MEM-2. Thus, repeating the index loading many times becomes the bottleneck of BWA-MEM-2's performance. In-memory index store of BWA-MEM-SCALE replaces many repeated index loading with one-time preload and removes the bottleneck. The third bar, BWA-MEM-SCALE with 73 GB of indices, shows the result with the exact match filter and FM index accelerator. The main performance improvement is from exact match filter, and total speed up is 3.2 times. In the last bar, with 121 GB of indices, enumerated radix tree is applied, and the performance improvement reaches 3.32 times. In our paper, there are many things not shown in this presentation. For the details, please read our paper. Let me conclude this presentation. In this presentation, I present BWA-MEM-SCALE, which accelerates the widely used genome sequence mapping program BWA-MEM-2 by up to 3.32 times. It exploits the remaining memory in the system by exact match filter, FM index accelerator, and enumerated radix tree, and exploits the whole CPUs by optimization techniques and in-memory index store. BWA-MEM-SCALE can run on commodity servers and does not require any special hardware. In addition, BWA-MEM-SCALE provides memory scalable performance for genome sequence mapping. It selects the best indices or partial indices with the given memory limit, and optimizes the overall performance with the given memory limit. Our implementation is publicly available on the following site. Please visit our GitHub repository. Thank you for listening.